You ever find yourself standing on a coastline and you look one way and see these massive cliffs that look like they've been there forever? And then you look the other way and the coast just seems to be, well, crumbling into the sea? It's a really cool puzzle. And today, we're going to dig into the hidden science that solves it. Okay, let's get into it. So on one hand, you've got these incredible, steep cliffs. They just look totally invincible against the ocean. And on the other, you see these soft, collapsing bluffs that seem to shrink back every time there's a big storm. And you got to ask yourself, wait a minute, it's the same ocean, it's the same weather. So what's the deal? What's the secret sauce that decides if a coast stands firm or just washes away? All right, so to crack this mystery, we've got to start at the most basic level imaginable. What is the coast actually made of? Geologists have a great word for this, lithology. And honestly, it's our first and maybe most important clue to understanding a coastline's real strength. Now, what's really fascinating here is you can see this clear pecking order of strength. Right at the top, you've got your igneous rocks, like granite. They've got this dense, interlocking crystal structure that makes them incredibly tough. Then you step down to sedimentary rocks, like sandstone. They're formed in layers, they're often full of cracks. They're basically giving the waves a roadmap of all their weak spots. And at the very bottom, you have what's called unconsolidated material, basically just clay, sand, gravel. They're loose particles, almost completely defenseless against the power of the waves. And this analogy just hits the nail on the head, right? It's one thing to talk about crystal structures, but it's so much clearer to just picture a massive stone fortress versus a sandcastle. One is built to endure anything. The other, well, you know it's not going to be there tomorrow. That huge difference, that's the power of lithology in a nutshell. But you know, the type of rock is really just chapter one of the story. The real plot twist is how those different rocks are stacked on top of each other, because a cliff's internal structure can actually become its greatest weakness. And this all comes down to a process called differential erosion. Okay, so picture this. You've got a cliff with a super tough layer of sandstone sitting right on top of a really soft layer of clay. Now, the waves aren't stupid. They know they can't do much to the sandstone directly, so they cheat. They just hammer away at that soft clay at the bottom, carving it out from underneath. This leaves that heavy slab of sandstone just hanging there in midair with nothing below it. Gravity and rainwater do the rest, and boom, the whole section comes crashing down. The strong rock didn't fail on its own. It was betrayed by the weak rock beneath it. And it's not just the ocean attacking from the outside. Rainwater can be like a secret agent, a saboteur working from within. Water seeps right through a permeable layer like sandstone until it hits an impermeable layer like clay, which is like a waterproof barrier. It can't go anywhere, so it just builds up, making everything soggy and heavy and creating this super slippery zone between the layers. It's the perfect recipe for a landslide. And the craziest part is, it's all happening completely out of sight. So we've talked a lot about the non-living parts of the coast, the rocks and the water, but the final and absolutely crucial piece of this puzzle isn't rock at all. It's alive. Vegetation can act like a natural, self-repairing suit of armor for the entire shoreline. You know, it's absolutely incredible to watch biology literally build geology. On a bare, sandy coast, these tough little pioneer plants like marram grass start to take hold. Their crazy complex root systems start weaving this net that binds the loose sand together, while their stems trap even more sand blowing in the wind. And over decades, this one humble type of grass literally engineers an entire line of defense, turning a flat, vulnerable beach into a massive dune system that can soak up the energy of the biggest storms. And you see the exact same idea at work in the calmer waters of estuaries. The heroes here are salt marsh plants like cordgrass. They move into these muddy areas, and their stems act like a brake on the water, causing all that fine silt and sediment to drop out and build up. They literally build the land up all around them, creating this amazing habitat that also happens to be a perfect natural barrier against erosion. Okay, so we have our three key factors now: the strength of the rock itself, the hidden weaknesses in how it's structured, and the living shield that can protect it all. Now, let's bring them all together and finally solve the case of the crumbling coast. And here it is. This is the big takeaway. A coastline's fate is never, ever decided by just one thing. It's always this interplay between these three forces. So you have to ask, first, what's its foundation? Is it a fortress of granite or a sandcastle of clay? Second, what are its internal secrets? Are there weak layers just waiting to cause a collapse from within? And third, is it wearing armor? Does it have that living, breathing defense of dunes or marshes? And look, this isn't just some cool science lesson. This knowledge is being used right now on the front lines of climate change. It's what lets us predict which areas are most at risk. It's what helps us design smarter coastal defenses. And ultimately, it's how we protect the communities that millions and millions of people call home. So the next time you're standing on a shore, you'll see it in a whole new way. Not just as land meeting sea, but as this incredible, dynamic story being written in rock, water, and life. A constant negotiation between these immense forces. And in a world that's changing fast, the real question is no longer just how this story goes, but what part we're going to choose to play in writing the next chapter.